Okay, so section D, calculus. Again, some things in this section will just not be easily done on a calculator. Sorry, I'll just get back to my screen. So let's have a look at it. The first one is an average rate of change. The best thing you can do is just do this manually, really. Again, you could do it if you want to. And I just wanted to point out that if you want to use, if you don't want to sort of go to the pain of using the fraction symbol, which, you know, is a bit tedious. What you can do instead is make sure you put brackets around stuff. So if I go minus 34 minus 6 in brackets and then use divided by and go 10 minus 0, then I will get the minus 4. It will put it into fraction format as well. So you don't have to. Don't forget your units as well, otherwise you will lose marks. Question 2 is just interpretation. Question 3, it says using calculus, find the stationary points of the function. So we should know by now that to find the stationary points of the function, we find the derivative and set it equal to 0. Now, can I suggest that finding the derivative of a polynomial function like this is trivial? You can use your calculator to do it, but I don't see the benefit because, you know, if you've forgotten the most fundamental power rule application of calculus, you're probably not going to do well in this section anyway, to be fair. But just for completion, I will show you that if I go, look, I'll show you this way because it is kind of useful. First of all, I'm going to define the function as, f1 of x, and then use my control less button here to get the defined thing. And I'm going to put in the function as it is. So minus 2x cubed minus 3x squared plus 36x minus 15, enter. Double check, 2x cubed minus 3x squared plus 36x. Okay, cool. So that'll be useful later on in the question. So I'll explain to you why I've done it a bit later on. Using calculus, find the stationary point. So find the derivative first. Like I said, you should be able to do that in your sleep. But you can go menu, calculus, derivative. And what I'm going to do here is I'm going to say dy dx, and rather than typing out that whole function, which I could do in this box, I'm just going to use f1 of x since I've already defined it up here. But you literally could write that in that bracket instead. Press enter, minus 6x squared, minus 6x plus 36. Hooray. But you should have been able to do that by yourself. You can also do this. Just be careful what you're doing. So I can go f2 of x is defined as, and I can put that in like so, and press enter, and that will define f2 of x as the gradient function of f1 of x, and that can be really useful as well. So again, if I just go f2 of x, it tells me it's minus 6x squared minus 6x plus 36. Now, stationary points occur when f dash of x equals 0. So what you do is you write down minus x squared minus 6x plus 36 equals 0. You can do things like factor. We're factorizing the gradient function, f2 of x, and that'll give it to you there. Minus 6 times x minus 2 times x plus 3, which you can then solve for x. You can also go solve the gradient function with respect equals 0 with respect to x, and that'll give you x equals minus 3, x equals 2. So that makes short work of this stuff. And then, of course, we have to work out the y coordinates and given the x coordinates. So now that we've got minus 3 and 2, I can go back to the original function, which is f1, and I can just put in minus 3, and I get minus 96. There it is there. Definitely wouldn't bother doing that. I would definitely just go f of minus 3 equals minus 96, bracket GDC if you want. f1 of 2 is equal to 29. There's the answer there. Again, wouldn't bother with that. I would just go f of 2 equals 29. And that saves you probably another minute or so doing like that. You can see here that in the solutions, the coordinates have been written quite clearly. You should do that as well. Just if you stopped there, that tells me that you kind of know what you're doing, but you don't know how to put it together. So make sure that if it asks for a point, you should be giving a coordinate. Y-intercept, x-intercepts, turning points, stationary points, they all should be written as coordinates. Using calculus techniques, determine the nature of the stationary points. Okay, so the approach you can't really get out of doing. So we're using what's called the first derivative test. So we've got x, f dash of x, and f of x as the shape here. So what we can do is on our GDC, now that we've done all this work, is that we can make sure that we are getting it right and not just pretending to know whether it's a maximum or a minimum. So you can see here the middle number is always the stationary point, or the x-coordinate of the stationary point, and then we choose any values to the left and the right. Doing it manually, choose a good value, like an easy value. But if you're doing it on the GDC, doesn't really matter, as long as, say, for example, the number you choose here to the left of 2 is not beyond -3. So it's got to be between -3 and 2. So I'll use the numbers here. And again, because we've done all that work in our calculator, it makes short work of it to confirm. F2 of -4 is negative. Negative. F2 of -2 is 24, is positive, -0, positive. And I would never do this in a test where time is a premium, but F2 of -3 is 0, just to confirm. Negative slope, flat, positive slope. Do the same thing for the other one. F of 2 of 1, sorry, F2 of 1 is 24, positive. F2 of 3 is negative. So therefore, this is a maximum, this is a minimum. Done. Okay. Sketch a graph. Well, we've pretty much got most of the information already. We should be able to sketch this, but I would not muck about. I would just go Control plus page, add a graph, go up to, this is the derivative, this is the actual function, press the right arrow to tick it. There it is there. Again, like I said in the previous video, I would much rather use window settings as my zoom so that I can have control over what I'm seeing. Just zooming in and out is not that great. So I can see I've got a maximum here of 29 all the way down to -96. And I don't know those yet. I'm just going from the values I know. 2, -3, -3. Okay, so I think I'd be going from -5 to 5, and then my y minimum would be -100 and, what was it, 29 there, so maybe 50. Okay, and I'll click out of that. There we go, that's pretty good. So there's my function there, which you can see is pretty much there. I think I stuffed this bit up. I didn't go far enough here because I didn't know that there was an x-intercept all the way over here. So back I go, window zoom, window settings, and I'm just going to change that to -10. Okay, oh, that's better, I'll say. And now I'm good to go. So then I will use menu, analyze graph 0. There are 3 of them. So what I'd probably do is I'd probably click on the lower bound, drag across to the right one, and then I'd write that down, -5.22. And then I keep on dragging until I get to the next one, and it's 0.437. So I'd write that down. And then I'd go to the next one. I haven't gone far enough, so it's not picking up on it. So then I just press escape and go menu, analyze graph 0, and then do the last one. 3.28. There you go. So they're the values. -5.2. Okay. Y-intercept, we should be able to figure that out probably from the function, -15. No need to waste time doing that. So I've got the shape from here. I know what my intercept, my turning points are from part A and B. I know what my y-intercept is because it's easy to get from the function, and I've used my GDC to work out the intercepts, the x-intercepts. Good to go. All right, question 4, the gradient of the normal. Okay, there's a bunch of things that we have to do here, and none of it is really useful to do on a calculator, really. You need to be able to work out the derivative of that. You can work out the derivative even though it's like got a k in it, but it's, I don't know. I feel like it's not really worth it. You should be able to do it without it. But calculus, derivative, d by dx. So that tells me with respect to x, and now I just put it in just like it says, 4x cubed minus kx squared plus 18x plus 30, return, and it gives me 12x squared plus 18. So it's just, it just hasn't even paid attention to the k, unfortunately. So as you can see here, then it does not work. So we would have to do it manually, or at least use it to confirm parts of it, but knowing that the term with the k in it's the bit that needs more attention. So I don't want to spend too much time on this. We're told that the normal, the gradient of the normal is -1/6, which means the tangent line has a gradient of 6 by, because if you multiply these two together, you get -1. Substitute 1 in for x, and then you can solve for k. I don't think there's anything really here for your GDC to worry about. This one here, determine the x values of the graph y equals -6x cubed plus 15, where the gradient of the tangent is parallel to the line. So you need to know that parallel means the gradient of this will be the same as the gradient of this at that point, which we don't know yet. So the gradient of this line here is -1/2. So we're really looking at when is the gradient of this equal to -1/2. So we set these equal to each other and solve to get plus or minus 1/6. Again, I think looking at these, it would be faster to do manually, but you could, if you wanted to, go to your old pal, the solver, and go -1/2 equals minus 18x squared with respect to x, and solve that, and you get x equals -1/6 and x equals 1/6. So those two solutions there. Notice it says x values, not points, which is why we only need to work out the x. Determine the derivative of this. It's worth 2 marks. So again, although the GDC will work out the derivative directly, what this is worth for 2 marks is, why it's worth 2 marks is because it's expecting you to say, well, power rule, how do I use the power rule? Only when terms are added and subtracted. So I have to expand this first, which is that line there, and then use the power rule. I don't think there's anything, I mean, you can confirm on your GDC, but that's about it. This question here proved to be quite challenging for students last year. So I'm going to concentrate on using your GDC and less on how to go about it. So there's the problem there. And it says you have to show that h equals 1440 minus 7.2. The only thing I can see really that you could use your calculator for is you get to this point here and you have to divide everything through by 2.5. So that's just straightforward calculator usage though, really. So then you can see that's 1440 and 18 divided by 2.5. Give you the numbers that you're looking for, 7.2. I guess if you want to be really exciting, you could go 3600 minus 18a divided by 2.5 equals, and it gives it to you like this, 7.2a minus, so it's not much easier really. Okay, part B, use calculus techniques to find the amount of gold. Again, it's got more to do with how complicated this is really. You could certainly get it as far as this. E is equal to this. You eventually have to find the derivative though, so you have to take it as far as this, and I don't think your GDC is going to help you much. You can use it to expand the top though fairly easily, so you can go expand 1440 minus 7.2a 100 plus a, so that'll go from there down to here at least. There's the minus 7.2a squared, there's the minus 7, the plus 720a, there's the plus 1440. I've got a plus 720a here. Oh, yeah, that'll simplify to 720a. And then you've got it sort of split all over hundreds here, but effectively I'd probably just be looking in that and saying, I have to move the decimal point a couple of times in order to get this solution here, which I don't think I can do easily. I'll try expand this divided by 100. There you go. So 1440 plus 7.2a minus 0.072a squared. I'd leave it like that. That's fine. But you can see that they've just led with a positive term and gone up in squares instead. And then you can find the derivative of that. Now, because it's got all decimals here, that might throw you off a bit. So it probably wouldn't hurt to just find the derivative using your GDC, calculus, derivative, dy by dx of this thing here, which I should have put into a function, but I haven't. So I'm just going to copy it, paste it. Oops. I don't know whether you can see why that was a problem, but it's a problem because I said d by dx, and then I've got an a in the equation. So I change it d by dA, and that gives it to us 7.2 minus 0.144a, and yes, that's what I got here in my solution, so that's good. So that could catch you up a little bit of time. It said use calculus techniques to find the amount of gold to spend on health to maximize the player's effective health. So E is the effective health. So I found the derivative, set it equal to 0, and solve. So I can go solve. B paste equal to 0 with respect to A, and I've got A equal to 50. So there you go, I've got A equal to 50, and if I need to work out the effective health, I can then put it back in. So a lot of this probably would have been a lot better if I'd sort of set up the equations at the start rather than just doing it all like this. Okay, and then the last one is justify the amount, and you can do the same thing again. You can just substitute values in and so on. So how I could have improved this is that when I know I've got to find out values and find out derivatives of functions is to set up the functions like I did here, and then I can use the functions over and over and over again. Okay, that's it for the 2021 exam. Please feel free to email me with any questions or anything that needs clarity.